of people asked me in the discussion after I spoke about the answers. So when I explained it verbally, I was correct about the second distribution is lower complexity, because it's kind of saying 50-50 for all the assignments. But on the slide, it's incorrect. Right? In the slide, I said that they were both the same. So I'll fix that in the slide, but just don't get confused if you weren't one of the people who came up and asked me. So yeah, that's something, just wanted to make sure it's clear. Yeah. And now we're going to do something a little bit different, right? So kind of up to this point, we've been building some sort of theoretical intuition about how this sort of variational inference idea is going to work, right? We've been writing some inequalities saying, like, if I have a mixture distribution, this is my likelihood. If I have certain assignment of probabilities, this is the more complex, this is the less complex one, right? So we've gotten some intuition for if I knew my parameters, or if I had a distribution over my latent variables, I know how to say which one is more complex or less complex. I know how to say which one has higher reconstruction error or lower reconstruction error. But I haven't told you how you would actually figure out Q, and I haven't told you how you would actually figure out theta, right? So how am I going to search, right? So we basically, in that kind of machine learning picture, I have the evaluation strategy, right? I know how I'm evaluating different choices of Q and theta. But I haven't given you a search strategy yet. I haven't told you how you're going to search through all the possible choices for Q and theta to get something that's actually plausible and useful in actual data analysis, right? So that's kind of the plan for the next large chunk. And this is kind of the area where there's a lot of research, actually. Like, this stuff I've told you so far is kind of, people understand this is the mathematical manipulations that we can do to understand evaluation, but the search strategies are much more open. It's not clear what's the best search strategy yet. But maybe a good starting point is this thing called variational expectation maximization. It's actually sort of intuitive. The idea is z and theta are giving you, they're kind of qualitatively different kinds of parameters, right? Theta, they're like my means for these distributions, right? The idea is, if I knew the latent variables, these are the just parameters of my different components that I would learn to fit. So, okay, that's like a global parameter, right? The idea is, like, you only have k of these means. You don't have n of the means, right? You don't have as many as you have data points. You only have some fixed number of mixture components ahead of time, right? The z's, on the other hand, you have one for each of the data points, right? So basically, in the original mixture diagram, right, the thetas, the mu's, these are like global parameters, right? These are the things that are, you only have a few of them. They're the centers of these distributions. But then the z's, I have one of them for every single data point, right? So it sort of makes sense to try to decompose your optimization over these two classes of things that you don't know, right? One of the things you don't know are these k component means, but these are kind of global information. And the other thing that you don't know are these zi's, like these assignments. And these are kind of local information, right? And the strategy in variational EM is to alternate fitting these two. So yeah, that's basically the idea. There's something called an E-step. What is the E-step? It fixes some configuration of the thetas, and it tries to find the right Q that's plausible, given that configuration of the thetas, all right? So the idea would be kind of here, if my means were over here and over there, then in my E-step, I would update the heights of my bars so that it puts more height on the bar for the one that's closer, the mean it's closer to, right? So that would be your E-step in this case. Your E-step in this case, it wouldn't really have any, it would try to maybe make a little bit of progress, but it doesn't have that much information. Your means are pretty close to each other, so maybe the one that is closer to it would have a little bit higher of a bar, and it might start to separate over time. But at this step, your Z update is going to be pretty small, right? But okay, so that's the E-step. And then the M step is like I fix my configuration probabilities, and I try to figure out the means which are most plausible, right? So again, kind of this picture, what I would do is I fix my heights of the bars, and I say, well, I'm going to take kind of a weighted average of the circles where my weights come from the heights of the bars. And then that is going to be where you put the mean for that component, right? So then the idea is like if you alternate these two kinds of updates, hopefully they give you reasonable fits. And you can even make this formal because we can compute the evidence lower bound, the elbow, for each of these configurations of theta and z, right? So we can make sure that our updates are actually increasing the elbow, right? In certain strategies, you would make sure, like in variational EM, the typical thing you would do is you would fix fix the thetas, and you would find the configuration of Q that maximizes the elbow over that one parameter, and then you would alternate, and then you would maximize the elbow over the other parameter. So you're kind of doing an alternating maximization of this elbow expression, right? So just back to that one. Basically, you have this quantity. You think of it as a function of both theta and Q, right? And in the first step, like in the E step, I fix theta and I try to find the optimal Q. So what is the Q that maximizes reconstruction without having too much complexity, right? So, and then in the alternating step, once I fix my Q, I differentiate this thing with respect to theta, and I try to find what is the best means so that I maximize this expression. And then iteratively, you're always increasing this lower bound, and the hope is that you find configurations of z and theta which have high likelihood overall, right? So that's the variational EM idea. And now, okay, so I haven't really defined variational inference. We've kind of been circling around the idea for a little while now, but now I'm going to actually define it in a little bit more formality, right? So I haven't really told you where do these Qs come from, and when I say that you're doing some sort of update for your Q, how do you actually update Q, right? Right now I'm just saying, like waving my hand, like you find the best Q, that's kind of consistent with the theta that you have so far, but you need to actually get numbers that you're going to put into an algorithm, right? So how are you going to do this? The idea is we're going to posit certain families of Q, and then we're going to do some sort of like a concrete update on each of the Qs, right? But first, what are the families that we're considering, right? So the idea is kind of even before I define like Q, this capital Q is like all the possible distributions that I can assign, right? So like in the previous one, it was all these different Bernoullis with different probabilities, right? Other examples, like in the beta Bernoulli one, Q would be the class of all the beta distributions, right? And then the idea is this defines a large family of possible Qs, and you're going to want to have one that's close as possible to the real posterior. But the real posterior is not necessarily going to lie in this family, right? So the intuition is that you have some kind of subset which you know how to navigate across, and you'll navigate it across it until you land somewhere that's hopefully close to z given x, right? So that's one thing. You need to figure out the navigation strategy. The other thing is you might need to fiddle with the Q, right? So maybe I don't want to consider all possible Bernoulli distributions, right? Or like you could define different kinds of correlations between the assignments, right? In the discussion I had so far, each of the assignments, they're being made independently of the others. But I could have defined an approximating family where it says, well, these 2 points always should have the same assignment, right? And that's a different approximation, right? So you need to somehow choose this, right? There are a few common choices that we're going to talk about, but this is one of the kind of modeler parameters. You have to figure this out on a problem-by-problem basis. Okay, yeah, so this is this idea. What is the Q that we're going to use? And then kind of how are we going to measure quality? I kind of already answered this, but more concretely, how are we going to search? Right? We have the evaluation, but how are we going to search for the right Q? Okay, so here are some examples that are common in the literature, but we're only going to talk about two of them. We're going to talk about mean field, and we're going to talk about, well, we already have this expression for the elbow. How are we actually going to use this to optimize things? So first of all, what is mean field, the mean field approximation? So I don't know. This is like, the word is not particularly expressive, but the way you think of it is, I have a configuration across all these different points. So this is the z1 to zn. And then you just decompose it. You say, okay, trying to figure out configurations across all the points simultaneously is hard. Maybe I should just try to figure out assignments on a point-by-point basis, right? You just consider each one independently from the other, right? And that's the expression on the right. So this is a little bit, this is like a smaller class of densities, right? Like in the example before where I want to tie together the assignments for 2 points, you couldn't, that would not work with a mean field approximation, right? Because the mean field, since I'm taking a product, it's like it's forcing independence in my assignments for each of the points. So there's no way of tying together 2 points because since I'm multiplying the probabilities, they're independent, right? Graphically, the way I would think of this is the one on the left is like this kind of complicated joint density across all the assignments, right? So you can model things which are like not necessarily aligned with axes, right? But then the thing on the right, this is just, these are just like a 1 coordinate at a time, the assignments, right? So basically, reduce the problem from thinking about the joint density across all the z's to thinking about each coordinate 1 at a time, right? So the thing on the right. The downside is, since you're thinking about each one independently of the other, that forces some sort of restriction on when you try to eventually look at the joint. Because since you're multiplying everything together, when you multiply together kind of 2 densities that are along the different axes, you can only ever get things that are aligned with the axes, right? You can't get anything diagonal anymore, right? So it's a reduction that you choose to make. Okay, so this is actually how you make the update. Do I have explanation for, okay, that's the derivation. But just let's think about how do you read this expression. So first of all, the inner term. This is x, zi, and then z minus I means all the other z's, right? So this is just the complete data likelihood, right? This is the likelihood of the points x that I observe and a particular configuration of the z's, which at this point I'm assuming, right? And what is this expectation? So this is an expectation over all but the ith coordinate. So the idea is, okay, we're trying to update the ith zi. So right, I have this large mixture of Gaussians. I have assignments for all of them right now, but I'm trying to update each one of them, right? Consider just one of them that you're going to update, right? So fix all the other assignments for now, and then try to change one of them. The way you're going to do this is just fix that one, and then average over all the possible zi's that you could have gotten for all the other points, right? So this is, you randomly sample a configuration for all the other points. That's what this expectation over q minus I means. Draw from a configuration over every but the one that I'm trying to update right now. And then when I average this, I can evaluate for like the sample of the assignments that I got this time around. I can compute my log likelihood in closed form, right? And then the thing is, since I'm averaging everything except for the zi, this ends up being an expression in terms of zi, right? Because everything else you averaged over. You plugged in, you sampled many of those other points, but you kind of fixed the one that you weren't averaging over, right? So the others, when you average over, they just become normal numbers. But then the one that you fixed, this is like a variable, right? So this whole expression is a function in zi, right? And as I change the zi's, I'm going to actually get different numbers out, right? That's what I mean by it's a function over the zi, right? And then once I draw that function, I just normalize it so that it becomes a probability density, right? That's what the proportionality symbol means, right? So I take that function, I divide it by its total mass so that it becomes proportional, or so that it becomes a probability density, and then that's the density that I declare this new point is going to have, right? So this is an expression that you can calculate, and it's an update of the ith coordinates assignments, right? So this would be, like here, it would be I fix the assignments for all the other Bernoullis, but let's say I'm trying to update this one, right? So I need to figure out, do I decrease this red, do I increase the green, or do I increase the red, do I decrease the blue, the green, right? And the way you're going to decide that change is you're going to average over configurations from the rest, assuming that they're the correct ones, and then you're going to plug them into the complete data likelihood, and then you're going to view it as how does that number change as I change the parameters for my, when I change the height of the red bar, right? And then when I increase the height of the red bar, this expression is larger, then that's going to put higher density on the zi at that place. Okay, and I think so that's what the expression is. It's actually also kind of useful to think about, so you have an exp and a log, right? Things would cancel out if it weren't for this expectation in the middle, right? So it's almost like thinking about a log likelihood, but then the expectation in the log, or this expectation kind of keeps things from canceling out. But in a way, it's like I'm averaging over all the other configurations. It's almost like a conditional, right? Okay, so this is the proof. Actually, yeah, I think we can walk through it. It's not that many lines, but it's kind of a bit more complicated that I can't make this an exercise, right? But what is going on? The first line, this is the elbow that we've been talking about all along, right? This second line, this is just rearranging terms. You can get this by writing the x given z as like x and z divided by z, right? And then when you have the log of the ratio, you subtract out a term, and then the KL term cancels with that new term that you had. So the KL reduces down to this expectation over Q. Okay, now this third line is the reason why we needed the mean field approximation, right? Q, remember Q of z is a product over each of the coordinates, right? So if I'm considering like the log of that product, that's like the sum of the logs, right? So going from this log Q of z to this summation over each of the coordinates, you wouldn't be able to do that unless you assumed that Q had this product structure, right? So that's actually kind of the key point of being able the mean field approximation, right? Because what had originally been a very complicated expectation is now a series of very simple expectations, right? An expectation over n coordinates is a lot harder to deal with than n expectations over a single coordinate, right? So this is kind of the key. The first part, all I'm doing is I'm using the law of conditional expectation, right? So I'm just kind of expectation of x is equal to expectation over z of expectation x given z, basically, right? now, this is the magical part, right? Just drop all the QJs which aren't the one that I'm trying to update, right? You can ignore them because you're going to be trying to maximize this expression over only the coordinate that I'm trying to update. So any other expressions that don't have to do with this coordinate that I'm trying to update, I can just ignore, right? But then this ends up being exactly a KL divergence, right? Because the KL divergence is the expectation of a ratio of logs, or a log of a ratio, right? And then if you look at it, right, this is like, and I've dropped all except for QI, then this is like an expectation over QI of this thing minus the log QI. And then imagine exponentiating this, right? So that it's like a log of an exponential of this expression. And then I have like a log of this exponential minus this log, and the log of a different, or this difference of logs is like the log of the ratio, right? So, I mean, it's actually not as complicated as what I'm explaining verbally when you write down the formula. But yeah, it turns out like this expression is actually just a KL divergence, and it's a KL divergence between these two expressions. And then this is where the update comes from, right? Because you are free to change QI however you want, right? This is the whole point. Is like I have this particular point I've fixed. I want to figure out what is the best update for my variational approximation at that coordinate. How do I make it as large as possible, right? I want to increase this evidence lower bound. The way I make it as large as possible is I make this distance as small as possible, because it's a negative, there's a minus sign on the KL, right? So you would set this QI to be kind of proportional to whatever this density is, right? Because then the KL divergence between these two expressions is 0. So basically, since the KL divergence always has to be positive, the best you're going to be able to do on this lower bound is to set it to 0, right? Because otherwise, minus of some positive thing is going to be very negative, right? And the only way and the way you set it to 0 is exactly you take it to be proportional to this thing on the right, which is what I said the update was in the first place, right? So it's not at all trivial, right? Like, even just rewriting this expression, it's not obvious that you would want to use this term instead, right? So like this is clever, right? But then at the end of the day, like it gives a very simple criteria for updating QI. And the criteria is just make sure QI looks like this expression. And this is how you would update your mean field approximation, right? You just go coordinate by coordinate, setting the QI equal to this particular expression. And each time I change my expression for one of them, it's going to affect all the downstream computation as well, right? Because like once I've fiddled with the assignments for one, that new assignment gets used in the next update for the next point, right? Because it's always averaging over all the other Qs. Yeah. So this is the kind of organization of the computation here. Okay, and now we move on to variational autoencoders, right? So, let me think. Let me start saying first, let's think of like some simple example, right? So right now I've presented this kind of coordinate update in all sorts of abstraction, right? Like this could apply for any kind of mixture model or like a latent variable model, right? But let's think about a simple case where, say, I'm gonna, like, before we had Bernoullis for each of the ZIs, you could imagine a situation where I have Gaussians for each of the ZIs, right? I could say that, like, depending on each x, my latent variable lands in some 2D space, and each one is associated with some Gaussian with some mean and some different variance, right? So this is a different kind of mean field approximation. You might want to use it in, say, like exponential family PCA, right, where you had the continuous ZIs instead of the discrete ZIs, right? Now, it's kind of a little bit too bad that you have to compute this sort of expression every single time, right? Even in this simple case, where I have like a very simple, like different mu I, different sigma I for each one of them, right? You can do the math in this case, right? Like you can take this expectation over all the other variables, you could exponentiate this, and you can find the density that's proportional to it, and you can write a program which is going to update each of these coordinates one at a time. But it's a lot of hand calculation, right? And it's kind of difficult to do this across a wide variety of problems, right? Kind of an even worse situation happens when you try to do a more complicated variational family, and you can't even write down this sort of update, right? Like you can't actually do this expectation. It just ends up being an integral that no one knows how to do, right? So the plan is going to be, let's give up on mean field, like full mean field inference. Like, let's come up with a proxy that is going to be kind of theoretically less nice, but computationally way easier to work with, right? And this is going to be the idea of the variational autoencoder, right? So as kind of the running example to think about, so imagine you have some, it's again like a kind of a latent variable model where I have some latent variables that are giving me concepts, right? So before I talked about like illumination or not illumination, here I'm thinking about like, I have some of my images are mountains, some of my images are trees, right? And the points for the trees are all kind of close together in this latent space. The points for the mountains, they're close together in the latent space. When I look at them as pixels, they might look very different, right? Just because like maybe they have different colors in them, they have different like pixel values, but conceptually they're very similar, right? So in the latent space, they're very close, even though in the pixel space it might be very far, right? But you can imagine some sort of complicated process where I go from this kind of semantic meaning for each of these underlying z's, and I come up with the image that corresponds with it, right? And that's kind of this forward process. Now, this is one of these situations where you can't actually write down the closed form updates, right? Because if you're trying to go from some low-dimensional zi's into this likelihood, or like into this image likelihood, you want your image to be very complicated, right? So you don't want to say, well, it's a mixture of Gaussians, right? Like mixture of Gaussians is way too simple for an image, right? So what you're going to do is you're going to have some complicated transformation of the zi's, which ends up leading to your image. And the way you define that complicated transformation, you can use a neural network, say, right? But then now that I've defined this complicated transformation, I have no hope of computing that expectation over this complicated function of x and z, right? So we need to figure out another way around it. Okay, so this is the idea. So you might imagine at the beginning, like trying to assign a different, so basically given an image, I can try to figure out what is a good sigma and a good mu for it, right? So this is the encoding step, right? The hope is that you would start with a whole bunch of images of trees, and then they would be mapped to Gaussians in the Z space, where if it's a tree, the Gaussian is kind of in the cluster of all the tree Gaussians. And if it's a mountain, it's kind of in the cluster of all the mountain Gaussians, right? And then, like, how are we actually going to learn that? The idea is we use another neural network, right? So the idea is in the forward direction, when I'm going from the latent space to the images, I use some complicated function like mu of theta and sigma of theta. And on the way backwards, I also use a complicated function like mu of phi and sigma of phi, right? And this is actually, we say things like, oh, if it's a neural network, it must be complicated. But this is actually simpler than what we had in, this is simpler than what we had in the mean field inference, right? Because in the mean field inference, when I figured out a mu or a sigma for each point, I was allowed to use a totally different mu, a totally different sigma for each point, one at a time, right? think about the Bernoulli example, right? When I had all these assignments for all the Bernoullis, each of those p's, I could figure out a different p for each of those points. And I didn't have to do any kind of sharing of information across those points, right? It's not like my probability for one of the points depended on the probabilities I was giving for the other nearby ones, right? But then here, you're kind of making a simplification, right? Instead of having arbitrary mu's, instead of having arbitrary sigmas, I'm saying that they're probably going to be similar to each other when their x's are similar to each other, right? So this idea of kind of restricting the full mean field approximation to be some sort of function of the original data, that idea is called amortization. And it's kind of the key idea in variational autoencoders, right? So yeah, but that in the end, that's what you want to fit. Okay, so now we've reduced the problem of figuring out the arbitrary q and the thetas to the problem of figuring out the phis and the thetas, right? So instead of like arbitrary parameters for each of these q's, I just need to figure out what is a function phi which lets me share information in my encoding in an effective way, right? But then from there, the idea is exactly just variational EM again. So how do you actually do this? So we have this evidence lower bound, right? This is the thing that we're trying to approximate. Or sorry, this is the thing that we're trying to maximize, right? Now, you could try to do this sort of like a, so let me step back. Like variational EM, we're alternating between update Q and then update theta, update Q, update theta. This is fine. Here we're going to try to think of it as like a gradient optimization instead, right? So it's actually, this is important. It's not exactly quite the same, right? So what we're going to do is we have this expression, the elbow, in terms of both theta and phi now, right? And we're going to figure out ways, like a small step in the phi direction and a small step in the theta direction that helps me maximize my elbow, right? So the gradients with respect to theta are usually pretty simple. So I'm not going to write that down right now, but the point is that since the expectation doesn't have anything to do with theta, you just move the derivative inside the expectation, and that's a pretty simple thing to do. You just average over the derivatives with respect to theta, right? The derivative with respect to phi, this is complicated. And why is it complicated, right? If I just exchange in the integration and differentiation, right, this part doesn't have anything to do with phi, so I just ignore it. But where I had been having an integral multiplying it by q phi, I now have the derivative of q phi, right? And this is no longer an expectation, right? When I define an expectation, it always has to be like a function times the density that I'm sampling from, right? But now this is not a density anymore. So I can't actually sample from the derivative of q phi anymore, right? This is not something I can approximate using data anymore, right? So this is bad news, right? This means you cannot just naively use gradient descent or gradient ascent on your elbow, right? So there was a very clever idea that helps make this amortization technique work. And this is called the reparameterization trick in the literature. The idea is, it looks kind of ridiculously simple, but it works. So the idea is, if I'm trying to sample something like q phi of like the encoding given my data, maybe all you can do is sample some random noise and then transform it into something that looks like q phi. So I think it's easier to think about in an example, right? So let's say I'm trying to sample from some mu and sigma, where both my mu and my sigma are parametrized by phi, right? This density depends on phi, right? And then we saw before that if I have a density that depends on phi, when I move the derivative inside, I'm now no longer sampling q, right? I'm sampling, or like I'm not just, I have a derivative around q. It's not just an expectation anymore, right? But what I do instead is I sample a random noise, epsilon, and then I map it by adding the mean and then multiplying by the standard deviation, right? And then when you add the mean and you multiply standard deviation, that turns you into another normal, and the mean and the standard deviation agree with what you had in the first part, right? The main point is that in the beginning, phi is a parameter of the density, right? Phi is somehow related to the randomness. But in the second one, phi is a deterministic, like it's a deterministic transformation of the randomness, right? The randomness is only in this first step, and that doesn't have anything to do with phi, right? The randomness, the randomness is just epsilon. The phi is only in this deterministic transformation, right? And I think it's actually, this is a little bit of a digression, but how do you think about transformations of variables, right? So like this, think of this as epsilon, right? I'm drawing from some normal 0, 1. If I mapped like an identity function, I would get a similar normal 0, 1 on the left-hand side, right? I map a point here, and then I go back here, and then I get another normal density. If I give it a very like horizontal, like flat line, it's going to concentrate all the mass around that kind of horizontal flat line, right? So I end up getting some narrow thing, right? And then, if I make it like very steep, then it's going to start spreading things out a lot, right? And that's exactly what this expression says, right? Like if I do sigma times epsilon, if sigma is very large, right, then my slope is very tall, right? So if I have, very high slope, then it's going to end up spreading out the transformed density. So that means it has higher variance, right? So I don't know. I just like to think whenever you see transformation of variables, think of like this sort of diagram, and then it helps you see. And the main point is like in this first expression, the randomness is kind of telling us the difference between like these different densities on the left. But in the second expression, I have all my randomness just in this density on the bottom, and I use phi to parameterize these different slopes. So phi is now about these slopes and no longer about these densities. So that's kind of the point. And why is that useful? This lets me take my gradient inside. And since this expectation, right, it no longer has anything to do with phi, I can just exchange, and I'm still sampling with respect to epsilon, right? So it's still an expectation, right? And this is a derivative of a deterministic function, right? Because, this is just a shorthand for the transformation that I drew before. But that's like the z's that I have, right? And since it's an expectation, I can estimate it by just drawing a whole bunch of the standard normals, these epsilons, and then averaging the likelihoods that I would have gotten, or like the gradients of these likelihoods that I would have gotten. But that's it. This lets you optimize the elbow, right? And I think this is all of variational autoencoders, right? Kind of, if we step back a little bit, the idea was we defined, we had like some original large family of Q, which we would call our kind of our mean field approximation, right? And each of these would have different parameters for each point. And then we said, okay, that's a little bit too complicated to do any coordinate updates. Maybe I can't actually take any of these expectations. Maybe instead of having a different parameter for each point, I share information across all the points by using parameters that are functions of the data themselves. This got you a lot of the way there towards being able to fit complicated models, but then we had an issue with not being able to optimize phi very easily, right? Because I can't just take the derivative when I have a density that depends on phi. But if I move the phi from the density into a deterministic function and have only randomness that doesn't depend on phi, then I can actually estimate that gradient very effectively, right? So this lets you optimize phi. The gradient with respect to theta is usually simple, so you can optimize them both at the same time. And it's just like the variational EM story, where you're optimizing both these thetas and these phis simultaneously so that you learn both a good variational approximation and a good kind of setting of the global parameters theta. And there's a few exercises I put on this spreadsheet so that it works out kind of a little bit more of the detail for some like specific examples. So like besides the Gaussian, there's some other densities that are useful to reparameterize. And I was kind of a little bit informal about saying the kinds of approximations we were making, right? We started with a mean field approximation, and then we relaxed the different kinds of parameters so that they're being shared, so that's another kind of approximation. But it's actually very useful to map out what are the kinds of approximations you're making and like what are the kinds of losses you're making at each point. And that's another one of the exercises. Okay, but that's VAEs. Now, just some cool examples, which I think are neat. And this maybe helps you build some intuition for like why would you ever care about doing this, right? So, what's going on? This point, these are the Z's. This is my latent code. Given each one of these, or this is like some sample from my latent code, say, right? Because remember, each one of these latent codes has a distribution associated with it, right? Given these points, I can kind of start sampling a whole bunch of x's given that z, right? So what's going on here is it's kind of finding in the latent code space how to separate out the different digits, right? And then, like, once I figure out that code, I can actually sample many different images that are kind of similar to the one that I originally encoded. What's potentially even more interesting is that I can go to new places where I never had any real data in that latent code, and I can sample images associated with that new place, right? So this is kind of the canonical, but really we know how to do things with MNIST. This is not super surprising. I think a more interesting example, this is something with drug discovery. So the idea is you want to have some sort of semantic latent representation associated with molecules. And this is actually a very complicated problem because how are you going to compare two molecules, right? These are, like, there's no natural distance on molecules, right? But what you can do is you can imagine having some sort of generative mechanism where when I'm lying in this part of the space, I generate one kind of molecule. When I'm lying in a different kind of the space, I generate another kind of molecule, right? And then if you can define that forward generative mechanism, then the variational autoencoder lets you reverse that. It lets you figure out this Q, which is the distribution over those codes given some observations, right? So it turns this kind of complicated space where I don't have a nice distance into the encoding space, where I have a very natural distance between the coded kind of semantically meaningful points. So that was kind of an interesting application. Okay, this is kind of closer to what I was talking about yesterday with the humanitarian AI, right? Is when you have a decision that you're going to try to help someone make, it's helpful to give them some sense of the uncertainty, right? And that's like the whole reason we're doing this Bayesian, like all this kind of math is to be able to do uncertainty quantification, right? That's why we're working with probability in the first place, right? With this application, what they were able to do, they had a data set where they took these tumor segmentation images, so the top left are tumor segmentations, and they gave the image to 3 different radiologists. And the 3 different radiologists gave different assignments to that, like where the tumor is, right? And in a sense, this quantifies the uncertainty about like where the tumor actually is, because if different experts are having different kind of opinions, then it means that like, there is uncertainty about where it is. And then they were able to come up with a model, so their model is the last one, where every time you draw a sample of the segmentation, you draw a slightly different segmentation in a way where the distribution over these segmentations looks like the distribution it would have been if it had been experts, right? And the way it's doing this is using a variational autoencoder, or like some sort of modification of variational autoencoder. So I thought that's kind of an interesting application. Again, like since everything is probabilistic, you can do things with missing data, right? So here is, in segmentation, you're given an image, an object's in the image, and you're trying to segment that object out. if you, and like, imagine you have a missing data scenario where like a lot of the pixels are just noised out. If you're doing an ordinary semantic segmentation method, it's going to be very confused by all this grayed out pixels, right? So here, it's not going to know, it's going to try to fit the grayed out pixels somehow, and that's going to lead to really bad segmentation results at the end. But since we're in a kind of probabilistic setting, we just condition on the information that we did see, and we just ignore the information that's not available to us. So we can still come up with a segmentation map, even though we haven't observed everything, right? And this is just kind of there saying that this is what happens if you just throw an ordinary CNN segmentation. It gets all kind of blurred out by the background noise. But then if you don't incorporate, if like you ignore the grayed out area, you're able to get kind of reasonable segmentations. And since it's probabilistic, you can get multiple segmentations. Okay, and another kind of interesting example, this is the one-shot generalization problem. So the idea is I give you some symbol, and you needed to generate a whole bunch of examples that are similar to it. And the reason people are interested in this is because in psychology, they do, or like cognitive science, they do a lot of experiments like this, and people are able to kind of, based on their knowledge about how symbols usually look, they're able to draw variations of that symbol very easily. But if you tell a computer to do this, all it's usually good at is it memorizes the one that it sees, and then it just copies that one over and over again. So that's not that interesting. But if you do something probabilistic, you can actually start sampling kind of variants of the original symbol that you saw, even though you only saw very few or even just like one example. So the idea is here you saw the top row, and then this is the kind of autoencoder learning to sample variants that are very similar to it, but which aren't exactly the same. So that's pretty deep. Okay, so this is kind of a crash course in a lot of Bayesian deep learning concepts. I know Dovan and like people will be covering in a little bit more detail in some of the previous or some of the later lectures. So kind of the main point I want to communicate. So first of all, like latent variables, they're a little bit more of a pain to work with in terms of optimization, but they give you a lot more flexibility, right? Think about, if you had only one Gaussian at a time, you would have to force like unimodal densities everywhere. But now, when I have a mixture of k Gaussians, I can get a k-modal thing, while most of my algebra is still related to Gaussians, right? So this is pretty unique, right? Think about how else would you specify a density with 4 modes, right? That's actually kind of complicated if you're trying to do it from scratch. But if you're doing it by mixing things over simple, like mixture components, then all of a sudden I can lift up my simple models into a complicated model just by introducing latent variables. So that's kind of one idea to keep in mind. And then this kind of other idea that appears over and over again is that there's some sort of qualitative difference between my assignments z and my global parameters theta, and you want to do some sort of iterative optimization, whether it's kind of thinking about it in terms of these gradients, like take like a derivative with respect to each one separately, or do some sort of EM thing. But the point is, figure out how to do optimization for thetas, and then figure out how to do optimizations for z's separately, and then use that to increase some sort of measure of the quality of your approximation. And then we have kind of a little discussion of variational autoencoders, where the basic point is that we retreat from the full mean field goal by amortizing inference over the parameters. Okay, and that's all for this section.
Yeah. So you mentioned that if the data is missing, we could condition only on observed variables and do inference, and this is a nice method that allows us to do that. But if there was informative missingness, so you knew how the data was missing, or if you wanted to learn something about the missing data, can you tell us a bit more about that?
Okay, yeah, so this is a good point, right? So when I say you just ignore the points that are not observed, that's kind of assuming that things are missing at random, right? If there's some structure, then you need to encode this somehow, right? The usual way you would do this that I know is you would try to actually build a model for how the missingness arises, right? So you would actually learn some sort of selection function, right? So maybe when you're in one kind of neighborhood, your data is more often missing than if you're in another kind of neighborhood, right? But this is kind of assuming that you actually have information for how you're informing the missingness, right? But yeah, I mean, on the one hand, this sounds a little bit more complicated, right? You have to introduce some sort of new estimation on top of what we already have. But on the other hand, kind of the good news is that by writing down everything in terms of a generative mechanism, we can actually kind of add on that extra component, which does this sort of selection step, right? And this kind of informative missingness step. And we can just tack that on to the original model, and now we can just estimate everything in one big model, right? So it's a little bit more complicated, but at least we have the language for answering that question.
On that optimization slide, still don't understand how we could optimize. I mean, I think that we have to choose the right kind of mixture of sphere so that the reconstruction error will go down. But how does the mixture of sphere, I mean the Q space is selected from that optimization? I still don't get it.
Okay, are you thinking of this slide?
Yeah.
Okay, so yeah, I guess this is one of these expressions that's always really complicated if you're thinking about it in the abstract. But I think it's helpful, I probably should have given some examples. So like, you can write down examples where it's like a Q are Bernoulli distributions, and Z are Gaussian, and then the X given Z are Gaussian distributions, right? Like kind of a mixture of Gaussian sort of setup. And then you can write down the likelihood, right? So that you can write down the middle expression in closed form, right? And then, like it turns out you can actually just, like this expectation, these are expectations over like product of Gaussians, right? Or like log of a product of Gaussians. You could actually figure out what the expression would be on the inside of this exp, right? So yeah, I agree it's not obvious at all. But then I think if you write down a specific density that's interesting to you, you're actually going to be able to take the expectation. I don't know, does this answer your question?
Because we increase the QJ, right, by choosing the right kind of mixture of Gaussian space, right? So that the reconstruction error will go down. Yeah. So we choose that sort of space while choosing from the mixture of Gaussian space, right?
Yeah.
But I don't see any value that represents that kind of space in that equation. So that.
Okay, well, but you are thinking about a likelihood, a complete data likelihood, right? So remember in the kind of the discussion problem where we were able to, when we had the separation into the two classes, that example had higher likelihood, right? So the same kind of phenomena happens here, right? Where it's going to prefer putting Zi in a way that's kind of consistent with all its neighboring Zi's, because that's going to have a higher complete data likelihood, right? So I think the answer to this particular part of the question is like, the way the other data points are coming into informing the update for Zi is through the complete data likelihood.
More questions? What course textbooks or other materials do you suggest for Bayesian deep learning?
Okay. So, I mean, Kevin Murphy has a very, very thorough book on just kind of all of Bayesian deep learning, but that's probably not the right way to learn it. I think, so there have been a few really good tutorials at the last few NeurIPS conferences. So I think that's one place to look. There's a really nice guide called Variational Inference, a Review for Statisticians by David Bly, which I recommend. And then kind of other materials. I think like for variational inference in general, there's a book by David Mackay called Information Theory, Inference, and Algorithms. So it's not all about this sort of topic, but it has a few chapters on variational inference, which I think are maybe the best exposition on variational inference that I've read anywhere. Yeah.
Okay. I see that lack of chocolates has dampened the number of questions.
Is there anything other than reparameterization trick for approximating gradients?
Well, I mean, there's like the classical reinforced trick, but that's considered kind of no longer so great, right? Or because that approach has a lot of variance. But there are actually quite a few kind of variations on the reparameterization trick which are being used these days because not all densities are reparameterizable, right? So there's some examples where you can try to do like numerical reparameterization, right? That was one direction I saw some people go. You can do, there's like acceptance rejection reparameterization. So it's like if you can generate things using a uniform variable through acceptance rejection, then it's as if you had had a closed form solution for the reparameterization trick. There's also recently a paper on implicit reparameterization. So the idea is kind of one of the exercises you'll see, one way to reparameterize things is to do the inverse CDF of your function on a uniform. But then differentiating an inverse CDF, this is complicated, right? So you can't actually take these gradients so simply. But there are ways to avoid doing that differentiation, which still lets you get the right gradient. So that's kind of recent research directions.
Okay, one last question, perhaps.
This is for page number 17 of your slide. 17. I kind of quickly went past. I mean, you were talking about some PhD thesis work that we could like. Could you name it again?
Oh yeah. So it's Shakir Mohammed's thesis.
Yeah, sure. Thanks.
Okay, so that was a very short question, so maybe we'll allow one more.
So in terms of the latent space, what would be like the, if we took just say the normal approach with deep learning and we had a feed-forward network and took the embeddings as a latent space, so is that a more constrained latent space or than assuming the distribution for the latent space?
Okay, so I think it's not necessarily going to be more or less constrained than the Bayesian approach, actually, because it actually turns out in a lot of situations the Bayesian approach and then the kind of optimization approach, where I have some loss function and I regularize it, these end up being dual to each other, right? Because regularization terms are kind of encouraging parameters to be like what the regularization wants it to be, which is similar to what priors do, right? So these have, or there's like a formal connection there. So if you regularize it in the same way, these are actually going to be very similar. Kind of the conceptual difference I would make between these approaches is that here I have very direct ways of sampling from like distributions over my parameters. So like for an embedding, I could get many different embeddings for that point, which are plausible under the data. Versus if I kind of am just running kind of standard optimization-based deep learning, you can try doing things with dropout. You can try doing things like bootstrapping it, basically. And that gets you something close to a posterior. But it's a little bit more heuristic. And there's not as much machinery that you have available for doing it.
Okay, let's thank Kris once more. So we have a bit more time for lunch, and we'll meet after lunch. Okay?
All right. The rest of the day is going to be kind of 3 smaller topics, along with the exercises associated with them. And the reason I'm passing out the exercises sheet right now is because during this talk, there are going to be a few gaps where I think I have exercise written for the GANs section, which I want you to try driving things yourself, and then we can continue with the talk. So that's the reason you can all get this sheet. So let's get started. This is, again, what is our goal in this talk? So first, I'm going to make sure that we kind of all get on the same page about the adversarial learning setup. This is one of these topics where I think you see a lot about people just using GANs all the time, and you see the results of these models all the time, but then you might not actually know how they're being trained. Like my experience is when people talk about it in more popular settings, they just talk about the application downstream without actually talking about what is the underlying kind of mathematical motivation for it. So I want to make sure that we kind of understand that. I want to give a few different kind of mathematical perspectives of GANs as well, because this is one of these areas where there's kind of several different ways of viewing the exact same procedure. And these different ways of viewing it are all sort of complementary, right? So if there's a certain kind of certain property that you want to derive, maybe one of these views is more useful than the other, right? And then I'll give a little bit of a flavor of real-world applications, but you're going to see more of this later in the course. Okay, so I'm guessing most people have seen these sort of images. The amazing thing, or like amazing to machine learners, is that these are all generated by a computer, but they look like real images of bedrooms, right? So like, yeah, it's probably the first thing that comes to mind if you think about GANs. Maybe the second thing that comes to mind is this image. Do people recognize this? Yeah. Yeah, that's right. This is the most expensive GAN sample of all time. So I realized like this is probably what comes to mind when you think about GANs. But I actually think this is not the most useful way of thinking about it. In a way, I might be a little bit unorthodox in my view of it. But like, I think the stuff about generating images is actually a distraction. I think like it's a distraction because the GAN idea is much more general, and it's actually much more deep than just, oh, we can generate all these cool images would suggest, right? The way I want to encourage you to think about GANs is they're doing some sort of unsupervised density estimation, right? Or they're letting you learn this kind of underlying manifold where most of the data lie, and letting you sample from that very effectively, right? So in a way, it's not really doing that much more than I have these kind of underlying points, and then I learn probabilities associated with all these points, right? So maybe out here is higher probability than kind of out in the outside. Now, this is like what's so interesting about this? Like we've been able to do density estimation for a long time. Kind of the most interesting things are that the way it's being trained is very different, and kind of you don't actually need a density. So it turns out in a lot of applications, and like one of the reasons it's been so successful is in the end you actually just need access to samples, right? And what GANs let you do is they kind of sacrifice access to these actual density, like probability values, for more, like the ability to sample more complicated densities, right? So that's why I'm trying to draw these kind of a little bit stranger, like you have islands out in the nowhere. Like trying to specify this in a formal mathematical function would be really, really complicated. But if you just need to define a program that can sample from that density, then you can write a program that samples from it much easier than you can specify a mathematical formula that will work. Okay, so again, to drive home this point that GANs are really doing density estimation. So you've seen pictures like this, I'm guessing, right? Where they start with one point in the kind of latent space, they get to another point in the latent space, and then you can kind of interpolate between them. And what's exciting is that each of these interpolated points actually looks like a plausible room, right? So that's, well, I guess that's one of the exciting points. The other exciting point is that none of these are actually, or like none of these intermediate ones are close to training data points, right? The reason they generated this kind of interpolation picture in the original DC GAN paper was that people were afraid that when they saw these samples that looked so sharp and they looked so good, people assumed like, well, maybe you're just memorizing the training data, right? Maybe these samples that you're generating, you're just kind of picking a random image from your training set and then producing it. But the fact that you can take two images in your training data set and then find a sequence of really good-looking samples in between those means that it's not just memorizing the samples, right? Because if it just memorized it, it wouldn't know how to go in between them at all. Right? So that's the whole reason for doing this interpolation exercise. But in terms of probability, right, I think the way to think about it is you pick these 2 points, and then you're finding some contour within the density which has, or like, has high mass, right? And you're kind of moving along points of high mass in this density, right? So even though like we've gotten so used to thinking about GANs in terms of like images, the actual principle is much more general, right? Okay, so this is kind of the first insight that the GANs people have, is since we're like our goal is to try to generate some complicated density, right? Or some complicated sampling mechanism. What's one way of generating a complicated sampling, right? One way is you start with something simple, you pass it through some transformation, and now you get something complicated, right? This is like the change of variables formula in probability, right? I start some density, I can write down a formula for the density of the function through it. And so this is actually now one of the exercises on the GANs section. So do you see the one about interpreting the change of variables formula? I don't remember which number this is. Or I can pull it up too. Okay, yeah, number 1. So maybe spend a couple minutes talking to your neighbors, sorry, and try to interpret the change of variables formula in terms of this picture. I think it's a useful exercise, and it makes the formula make a lot more sense afterwards.